So this is a talk about a picture I took recently of the Andromeda galaxy, and being quite a large target, something like 6 times the diameter of the full moon, it's well suited for smaller scopes. But I really wanted to get as detailed an image as I could using my 8-inch Newtonian and a 9-panel mosaic, and then to see what types of objects could be found in the image. And the reason I've called it a Philatelists guide is I guess that the talk has got more in common with stamp collecting or the cataloguing side of things than scientific nuts and bolts astronomy. So apologies to any scientists. For any new folks, M31 can easily be found by locating the W shape of Cassiopeia and then following the most obvious V path down 20 degrees to the nearest bright star, Merak, which is magnitude 2, and then back up towards Cassiopeia via the two fainter stars, Mu and Nu Andromeda. The galaxy itself is the most distant naked eye visible object at about 2.5 million light years away. It's the closest major galaxy to the Milky Way, and it's travelling towards us at about 300 kilometers per second. From Leeds, the bright core can be seen as a faint fuzzy patch in binoculars or a scope, but it can't be seen with the naked eye. We first saw the galaxy in Kilda when Eric and I were first starting out in 2018, and on the left is a 20-second exposure using an old compact digital camera on a static tripod, and you can see M31 there. On the right is one of my first attempts at astrophotography from 2019 with a DSLR attached to a 6-inch Newtonian. A couple of years later I had another go, this time as a mosaic with an 8-inch Newtonian and a recently acquired cooled Astro camera, but I only got short exposure times on each of the panes, around about 30 to 40 minutes, and the camera was badly positioned on the focus tube, so it meant having to take 12 different mosaic panes to fill in all the gaps. And then processing wasn't so many different bits, and stitching it all together wasn't particularly straightforward. So the aims this time were to do better and hopefully get increase the exposure time, and also to see if I could find any of M31's globular clusters, and then if the image was good enough to get a metal print. And by the way, the link to the full-size image and any internet URLs will be linked in the YouTube description below. And the gear used to take the picture included this Skywatcher 200 PDS, an EQ6 mount, cool color Astro camera, and an off-axis guider with a small mini camera. The theoretical resolution, not accounting for the Baade matrix in the camera, works out around about 0.77 arcsecond per pixel, and the guiding typically I get between about 0.4 to 0.8 arcseconds RMS. And because of the problems I had in 2022, this time I made sure that the camera rotation in the focus tube was properly aligned so I wouldn't get any gaps in the mosaic. I checked the camera orientation using the ocular plugin in Stellarium, and then just double checked that what I was seeing in Stellarium matched what I was getting on the images. So the mosaic consists of 9 images all stitched together. And to even out the variation in sky brightness due to target position and moon phase, I took the individual mosaic panes in 1-hour blocks and then juggled the scope position around to get the same effective exposure time, or more or less, to get similar signal to noise ratio. I had hoped to get 9 to 10 hours per pane, but with the weather, I'm afraid I only got the equivalent of roughly about 3 hours. And after the first 9 hours of exposure, I did a quick pre-process on each section and then a rough mosaic to check that the overlaps were going to be okay. And this is just showing a simple screen stretch across the result as a whole. And then it was just a case of ploughing ahead. And so after about 5 to 6 months, I managed to get in 17 nights and around about 47 hours of total exposure time. And this was the result. And it's quite a big picture. At the kind of resolution you use for a magazine print, it would be around about 1.4 meters by 0.9 meters, and it's got over 180 million pixels. I had hoped to get more blue in the outer regions of the galaxy, but that wasn't to be, and had to compromise on the fainter edges a bit due to discontinuity in the background on the mosaic panes. But quality-wise, in comparison with the 2022 image, the noise is a lot less. There's a lot more of the fainter details visible, and around the periphery of the image, the stars are a lot rounder as well. So I guess the next question would be to see if I could find any of M31's globular clusters. Fortunately, there are lots of catalogues from the scientific literature online, And M31 has had numerous cataloguing systems of its globular clusters over the years. I think Hubble was the first person to publish a paper on them in 1932. I picked this one from 2010 by Peacock from the Strasbourg Astronomical Data Center, or CDS, and it's got 416 old clusters, 156 young clusters, and 373 what they call candidate clusters. And to get the data, you just click on the Visio link and then pick the columns that you want and then sort of export it to a text file. And the text file, you can then put that into Excel, and you can filter and rearrange the columns and save it as a tab separated file. So in this case, I was only interested in the items listed as globular clusters. The data can then be plotted onto a plate solved image in PixInsight. Just to make it a bit clearer, in red are the old clusters, which are probably about the same age as the galaxy and distributed mainly around the nucleus. In blue, the young clusters, which are relatively blue in colour, are mostly in the outer star-forming regions of the galaxy. And then there's the candidate clusters, which may or may not prove to be globular in green. The young clusters are thought to have been probably accreted from small proto-galaxies and are 1 to 2 billion years younger than the galaxy itself. And this is a close-up view, and you can make out the extragalactic globular clusters, though you can't really differentiate between them and the foreground Milky Way stars. All but a couple of clusters in the Peacock catalogue were, however, visible in the image. And if you want to get beyond the object spotting or stamp collecting, web search will bring up several papers on the globular clusters, including this one from China. And this one used the Large Sky Area Multi-Object Fiber Spectroscopic Telescope, or LAMOST for short. And in the main plot, the colours are plotted in reverse. So the older clusters are in blue and the young ones in red. And you can see that some of the older clusters are at quite large angular distances from the M31 core. Which brings us to G1, or Male 2, which is the brightest globular cluster in Andromeda. It's 130,000 light years from the core and consists of at least 300,000 old stars. It was identified as a possible globular cluster in 1953 by Nicholas Male and Olin J. Eggen using a plate taken 5 years earlier with a 48-inch Schmidt-Cassegrain scope at Palomar in California. Now, I wanted to get a photo of this, but as it was outside the Mosaic area, I just took a 1-hour excursion. And also the main image just shows the state of play shortly after assembling the Mosaic panes, but with a large screen stretch applied. And if you look closely, you can make out the joins in the Mosaic on the columns there. And also there's a couple of artifacts which I think come from second order diffraction effects. And here's the G1 image after processing. And if you can't see it, G1 is that little dot in the center. And zooming in up close, you can compare with the Hubble Space Telescope from 2002, and you can see that the surrounding stars are reasonably round, but the globular cluster itself is quite elongated, which matches what you can see in the Hubble Space Telescope image. Now, I presume that the elliptical appearance is due to having gravitational interaction with the galaxy itself, which is something you see with some of the Milky Way clusters, but not to the kind of extent that you see here. And NASA reckons that there's a medium-sized black hole at the center of the cluster. There's also these two faint blobs in the image, which are listed as globular clusters, but appear to be quite diffuse. And it turns out they are in fact extended clusters. They were discovered in 2005 during a survey of M31 by the Isaac Newton Telescope Wild Field Camera in the Canary Islands, and the items that we can see in the picture are listed as C1 and C3 in the paper. They consist of at least 100,000 stars, and they're much larger and more spread out than regular globular clusters like those you can see below. And they reside in a spherical halo 200,000 light years from M31's disk. And as of 2005, there are no known analogues in the Milky Way. I also wanted to mention this Hubble Space Telescope mosaic, which consists of an incredible 411 mosaic panes with nearly 7,400 exposures and covers a span of about 61,000 light years across M31. And if you go to the ESA Hubble URL at the bottom, then you can zoom in on the mosaic, and it's well worth looking at. So this is just an example showing one of the globular clusters from the Hubble Space Telescope and the corresponding image from my picture. So what else can be identified in the photo? Well, the obvious thing to look for is the distant galaxies. And in PixInsight, there's the PGC catalogue with the principal galaxy catalogue, and that brings up 117 faint galaxies, of which 112 are visible. And 37 have got radial velocity on Simbad, and they work out in about an average of 1.2 billion light years, with the most distant being around 1.7 billion light years. There's also a few galaxies of note. There's Andromeda 4, which was discovered in 1972 by the Dutch-Canadian astronomer Sidney van der Berg when he was searching for dwarf spheroidal companions to M31. Thought for many years to be a satellite of Andromeda, the Hubble Space Telescope has recently shown it's actually a solitary irregular dwarf, and so it's just a line of sight coincidence to the galaxy. And then there's PGC 2314, which is quite a nice looking spiral galaxy, but obviously needs more exposure time and probably a longer focal length, and that's 260 million light years away. And then there's M32, a compact elliptical dwarf galaxy, obviously a satellite of M31. It consists now of older red and yellow stars with no current star formation, and it's ended up in its current form owing to interaction with Andromeda, having passed through the disk and lost many of its stars to a galactic stream which surrounds M31. It's also responsible for some of the features you can see in Andromeda and one of several of its satellite galaxies. There's also NGC 205, aka Messier 110. This is a peculiar dwarf elliptical. It's called peculiar because of the new hot blue star formation that you can see in the center, and also a couple of dust patches as well. It was only added to the Messier list in 1967, although Charles Messier drew it as part of a sketch of Andromeda in 1773. I think it's got a much lower mass than M32, and it's not thought to have had as much of an influence on M31's current shape, although it did affect the kind of warping of the galaxy's edges. There are also many other unidentified background faint fuzzies which I can't find in any catalogue. This unknown object on the left here, it is visible in the image in surveys in Aladin, including the Sloan Digital Sky Survey, but I've not been able to find any explanation of what it is. I presume it's a gravitational lens effect. PixInsight also has the milliclass catalogue, the million quasars catalogue, and shown here are just the visible ones. Many more either can't be seen, or because they're too faint, or haven't been plotted to avoid overlapping labels. In total, there's 328 quasars visible in the image, and 44 of those have got radial velocities on Simbad, and they work out to be an average of 9 billion light years away. There is, however, this one down here in the corner, which works out to be around about 12.4 billion light years. Now, having looked at the globulars and the usual background stuff, I thought about having a look for any variables. And as Ray mentioned last month, this is the H335H plate, which Edwin Hubble first realized showed a Cepheid variable instead of a nova in October 1923. And using the brighter stars in the image, it was possible to star hop to the variable location in my image. It's one of two variables which Hubble discovered in 1923, and by the time of his 1929 paper, he found 40 confirmed Cepheids and another 10 variables, and it makes up this kind of triangle pattern. So the question is whether it would be visible or not. So here's the same star hop pattern, and the Hubble variable is somewhere around about there in the image. So zooming in, you can see that the three stars are here, and that is the variable star in question. And here's the Hubble-spaced image of the same variable. Now, when I first looked at this, I got it wrong because I thought that it was indicating that the variable star position was here, and then the arrow was pointing to the exploded view. But it doesn't appear to be the case, because if you rotate it round, you can see that the arrow is actually pointing to the variable position, and then this exploded view is just sort of positioned so it doesn't sort of interfere with the satellite galaxies. So similar to what I've done with the globular clusters, I found an online catalogue of extragalactic variable stars and filtered those for just those in M31, and then plotted them in PixInsight and got this kind of weird distribution. So you can see that there's a bunch down here, a whole bunch up here, a lot on the left side of the galaxy, some in the center of the galaxy, and hardly any on the right hand side. And looking up the variable stars on Simbad, they seem to be different types in different areas. So in the center of the galaxy, in the catalogue. Most of them are classical novas, which I wouldn't really wouldn't call sort of periodic variables because most of them tend to go blip once. Um, and then in white are the classical Cephids, which tend to be the brighter Cephids. And in red are they're either listed as variable stars or the regular Cephids, which are the dimmer Cephids. And then in blue are the various other sort of esoteric types, which include the supergiants, which are quite bright. Now, most of these aren't visible actually in the image because they're sort of magnitude 25 or so. Eliminating any which are fainter than magnitude 21, and then taking out any which aren't visible in the image, these are the ones which remain, and they all are visible. And you can see it's mainly sort of the classical Cephids in white, and a few of the supergiants and the regular other types. If you look at the distribution on that, you can see that around about 20% of the classical Cephids are visible, but much fewer percentage-wise for the variable stars and the regular Cephids. But the kind of supergiants and some of the other types tend to be quite noticeable in the image, and they tend to be because they're the brighter stars. This is a close-up view just showing some of the variables that you can see in the image just to show that they're actually there. So a lot of them are really faint, but they are definitely there in the image. And the reason we can see them more often those than the other ones is that the ones we can see, like the supergiants and the classical Cephids, are on the top end of the color magnitude diagram, so they tend to be the much brighter stars, whereas further down the instability strip, we see far fewer of the other types of variables. So what else could I do? Well, Professor Paul Hodge of the University of Washington wrote a couple of books on Andromeda, including an atlas in 1981. And fortunately, the atlas is now online, so it was possible to align the plate images from the JPEGs and the website to the image in Photoshop and then look for the locations of the objects. And the atlas has got basically OB association, so that's the hot O and B type stars which were in open clusters and have since dissipated, but you can still tell that they were in an open cluster once upon a time. It's also got some globular clusters, dust lanes, and also open clusters. So this is just a sample area just showing some of the OB associations in red, and then some of the open clusters in blue. And the open clusters really are just faint smudges, but it's still nice to be able to pick them out. One of Professor Hodge's later papers includes this 2011 study which looked at the spatial relationship between the OB type stars and hydrogen alpha regions, and they basically showed that the kind of emission nebula that we see in the Milky Way you can also see in the Andromeda galaxy. This is one of the examples in the paper which shows a giant hydrogen bubble, and basically you've got OB stars in the center, and then the stellar wind from those has cleared a patch of the hydrogen alpha, and then you've got the excited hydrogen alpha gas around the outside, and this is just from the paper itself. So having found globular clusters, variable stars, some open clusters, and the emission nebula, I guess the next thing to look for would be planetary nebula. It's probably a bit of a tall order, but a few can still be made out. There's around about 50 so that you can see in the image, but they're just really just individual pixels almost. This is an example of one. And here's another. Now, when I was processing the image, I saw a few green stars, and I thought I'd really messed up the color calibration. But it turns out they're actually O3 emissions from planetary nebula, which I think is quite cool. And here's just a few more examples. Now, some are more believable than others. I think this one looks a bit dodgy to me, but some others you can definitely sort of say they're planetary nebula, which is good. I then tried comparing my image to one of the Spitzer's infrared space telescope images, which were taken in 2004 and published in 2005, and they used the multiband imaging photometer at different wavelengths in the infrared. And they basically showed that the structure of the galaxy consists of two logarithmic spiral arms with a circular ring of about a radius of about 10 kiloparsecs. And also the nucleus in the center is offset from the outer ring, which was quite interesting. They also worked out that the the star-forming ring is very circular, except for a region near M32 where it splits. Now, the images aren't quite aligned, but it's possible to trace out the dust lanes between the two. Flipping between the two images, it makes it a bit easier to make out the dust lanes. And it's possible to do a similar kind of thing with the UV in the UV using the NASA Swift UV satellite image from 2008. And this is a composite showing around about 20,000 UV sources. And obviously shows the regions of new star formation with the hot young blue stars. And you can see like the NGC 206 star cloud down there, and also some star formation in the outer ring. Now, when I talked about the extended globular clusters, I mentioned the Isaac Newton telescope wide field camera on the Canary Islands and the study that was made of the stellar halo around M31. And they basically found that the substructure pointed to a history of accretion and disruption in the galaxy. What was interesting was that the kind of spectral fingerprint, if you like, of the stars in the stellar halo, some of it matched what they found with M32. So it looks like M32 is probably a spiral galaxy to begin with, and then it's interacted with M31 and been turned or converted into a dwarf elliptical. But many of its stars have been left behind in the stellar halo, which was visible in this survey. And it is extremely faint. The stars, in the outside in the green here, around about sort of magnitude 30 per square arc second, so it is incredibly faint. Going back to the Spitzer infrared image, the paper which this came from compared computer simulations of the M32 encounter with the computer model, and basically they used some deprojected images of the disk, assuming an inclination of 75 degrees. So I thought I'd have a go at the same kind of thing. Now, to get a deprojected image of the galaxy, the first thing to do would be to rotate the image around so that the major axis appears more or less horizontal. And then basically our view of the galaxy, we're seeing it, at an angle. So it's actually lying at an angle of about 75 degrees to the vertical to us, and we're of course seeing it in this kind of plane down here. So what we'd have to do is to take the stars off the image first of all, and then to derotate it. And so this is the starless image, which has been deprojected by 75 degrees. Now, of course, it's not perfect because the image is actually a 3D object and you're treating it as a 2D object. But it gives the appearance roughly as what it would if it was actually a face-on spiral rather than being inclined at an angle. And you can compare it then to the corresponding images from the Spitzer paper. And the results compare quite well with the Spitzer images from the paper. And the paper backed up their images with some computer modeling, which basically sort of showed quite a decent correlation between the model and the actual results that they were getting. And I think basically they showed that M32 looks like it's passed through the galaxy ring. And in doing so, that's responsible for the split in the ring that you can see, and the NGC 206 star cloud that we can find. And I think they also indicated that the offset of the nucleus of the galaxy also was related to M32 passing through the galaxy. So nearly finished. I just wanted to mention the O3 cloud and hydrogen alpha image by Bray Falls, which James talked about on the LAS chat line. The O3 cloud was obviously the winner of the 2023 Greenwich Museum's photo competition by Marcel Dressler, Xavier Strotner and Jan Sainty. And at least the first two of those, they've had some sort of planetary nebulas named after them as well. And I think they all sort of specialize in taking very, very long exposures, sort of 1,000-hour type exposures in narrowband. And this is kind of, the images that we're getting. Now, the O3 cloud, I've seen a couple of papers on it. One was suggesting that it might be actually a supernova remnant in our own galaxy. Because they worked out that it was expanding at around about 94 kilometers a second, but they haven't been able to find out any other sections of the arc or the progenitor star that would be responsible for it. There is an interesting sort of, in Bray Falls image here, sort of an interesting sort of O3 patch which is just underneath M32. But I really wanted to mention this image because of the hydrogen alpha which it shows, because NASA about 2020 published this article which showed that there's a nearly invisible halo of diffuse plasma with a radius around about 1.3 million light years, so about halfway from Andromeda to the Milky Way. And I guess it kind of shows that if you go deep enough with these images, then there's a good chance that you're going to strike hydrogen alpha. And it's actually a layered structure with two distinct shells of gas, and it was investigated by looking at the absorption of light from quasars. And just to finish, as I mentioned at the beginning, Andromeda is approaching us at around about 300 kilometers per second, and NASA did some computer simulations derived from the Hubble Space Telescope data. So keep in mind how the interaction between M32 and Andromeda has made M32 into a dwarf elliptical, and also consider that if we think light pollution is a problem now, spare a thought for whoever or whatever is trying to do astronomy in the distant future from another planet somewhere in the Milky Way. So this is the present day. And 2 billion years time, 3¾ billion years, then slightly later, and slightly later still, and then about 4 billion years, 5.1 billion years, and then finally 7 billion years. And that's it. So thank you very much.